Welcome to the video key for quiz 3. Consider the reaction below. The temperature is 25 degrees C. All right, and we are supposed to calculate some thermodynamic parameters, delta H standard, delta S standard, delta G standard. All right, and to do this, we're going to have to use the equations on our, the data on the equation sheet. So let's go ahead and see how we do this. So with all of these, what we're going to do, all of these questions really are the same, is we're going to sum up the enthalpies or entropies for the products and subtract the enthalpies or entropies for the reactants. So we could say that if we multiply each thing by its coefficient and we look at the, for instance, the heat of formation of each substance, we're just going to add those up. And the little nu is the coefficient. And what we said in class was that the nu is positive for products and negative for reactants, so it's products minus reactants. So if we play this out specifically for this reaction, what this means is that we're going to take each product, in this case there's just one, so we take the heat of formation of our, it looks like this is oxalic acid, and in the solid state. I'll put a solid on here, and then we're going to subtract the heats of formation of each reactant. So we've got the heat of formation of ethylene, and then the heat of formation of our other reactant, but we're going to multiply by 2, so let's put that 2 in here. And we've got oxygen gas. Now oxygen standard state is as a gas, as a diatomic gas, and any element in its standard state, the heat of formation reaction would just be oxygen being formed from oxygen. That's got a heat of formation of 0. So all elements have a heat of formation of 0. So let's plug in the numbers here. So the heat of formation of oxalic acid is negative 829 kilojoules per mole. And we have to subtract the heat of formation of ethylene, which is a positive 227 kilojoules per mole. And so that ends up being a negative 1056 kilojoules per mole. Oh, I should point something out here. I think I wrote it on most of the quizzes, is please write kilojoules this way. So a kilo is always a lowercase k, and a joule is an uppercase J. So lowercase k, uppercase J. Okay. All right. So that's our first answer. And the entropy calculation is very similar. We're going to sum up the products and reactants and subtract the entropies of the reactants from the products. We're going to multiply by the coefficients. We have to be a little bit careful on this one. There's a pitfall that some of you fell into, is when we add this up, we're going to have the standard entropy of oxalic acid minus the standard entropy of ethylene gas put a solid in here, and twice the molar entropy of oxygen gas. And notice these aren't delta S's, these are S's. These are the actual entropy of the substance. And so the entropy of oxygen gas is not 0, so it's not like a heat of formation. It's not going to be 0. You're going to have to include it. So all these things are things that were on the equation sheet. Let's put them on here. We had oxalic acid solid is 116 joules per mole per Kelvin. It's a pretty low number because it's a solid. If we look at the acetylene, it is, oh yeah, I said ethylene. It's acetylene. It's C2H2. Anyway, the acetylene is going to be 201. So we're subtracting the 201 joules per mole per Kelvin because it is a reactant. And then twice the entropy of oxygen, and that's 205 joules per mole per Kelvin. And that comes up to a negative 495 joules per mole per Kelvin. And we should stop here and say, do we expect delta S for this reaction to be positive or negative? So we should be able to make a qualitative prediction just by looking at the reaction, seeing what's the relative moles of gas for our reaction. And looking at this, we've got, in the first reaction, we have a mole of gas here, we have 2 moles of gas here, and then no moles of gas on the right. So we're taking gas and just turning it into a solid. So we expect this should be a negative change in entropy, and indeed we got a pretty big negative change in entropy. Delta G. So delta G standard we can get by combining delta H standard and delta S standard. And whenever there's something like this where you're using prior answers, I'm going to just assume that your delta S and H are right when I grade this last one, so the errors don't cascade. So if you see OK and your answer's wrong, OK just means that your answer would have been right if you got A or B right, but you did all the math for part C right. Okay, so if we plug in our numbers here, we've got a negative 1056 kilojoules per mole. And what I'm going to do is write that out as joules per mole. And I'll show you why in just a second. So I've got my delta H standard, I've got minus T, and somewhere in here we have the temperature being 25 degrees C. Now, you don't want to write 25 degrees C because we want these units to work out, and entropy as units of joules per mole per Kelvin, not per degree C. So let's put in our kelvins here. We'll convert 25 degrees C to 298 kelvins. Oh, and a note about symbols here. Kelvins are an uppercase K, so you want to have you want to use uppercase K, not lowercase k for kelvins. And you also you don't have to put don't put a degree sign. It's actually incorrect to say a degree sign. So you don't actually say degrees Kelvin. I've actually seen that in a few science books. It's actually wrong. We just say kelvins. Okay, so we've got our negative T, and then we're going to plug in our delta S, which we said was a negative 495 joules per mole per Kelvin. So notice that the kelvins are going to cancel, and that's going to give me joules per mole, which is why I converted the delta H to joules per mole, because we have to make sure everything's on the same footing before we add or subtract. We can't add kilojoules to joules. That wouldn't work. Okay, so we add these numbers together, and we get negative 908. So notice we've got a negative number, and we've got a negative times a negative on the right-hand side, so it gives a positive. So that's going to eat away at our negative numbers here. So we get negative 908,000, I'm just rounding here a bit, joules per mole, or we could just put that in a more compact notation, say negative 908 kilojoules per mole. So you always want to check your energies, and your enthalpy should be in terms of joules or kilojoules per mole, in this case per mole, and your entropy should always be joules or kilojoules per mole per Kelvin. Okay. All right, last question. So this one is a symbolic derivation, and as I mentioned during the quiz, I thought the wording was a little bit unclear here, and so if you change that to delta TW, I didn't subtract for that. The main thing here is to see that there's only going to be 2 heat terms. Let's see what I mean. So let's draw a substance that's going to melt, get hot and then melt, and then heat up the liquid, and then boil, and then heat up the gas. And figure out where we are on this curve. Okay, so we have some water vapor that's already at 100 degrees C. So we'll go ahead and label this as gas, liquid, and solid, those little the slanted parts. So if we have water vapor, it can't be in the middle of this line, because that would mean that we have a mixture of liquid, and I'll make this a little more exaggerated here, there we go, liquid and gas. We don't have a mixture of liquid and gas in this half of the system. This half of the system is just water vapor, so we're going to say we are here. So that is that, and let's use a different color for the other part. The other part, it says we've got water that is below the boiling point of water. So the water is down here, right? It's not at 100 degrees yet. And we're told that not all of the water vapor condenses. So some of it does. So we could show that by moving like this. We're not going to condense it all the way to liquid. So maybe half of it or a quarter of it, some proportion of it is going to condense. So if it doesn't condense all the way, if there's some water vapor left over, we can't get off that line, which means the final temperature is going to have to be 100 degrees C. So we know this other one is going to go up to here. So we've got two arrows, okay? And they're going to, once both halves of the system are at 100 degrees C, we can't do heat transfer anymore, okay? So we're going to end up with a mixture of some water vapor and some water, but everything's at 100 degrees C. All right, this is like a little bit too, I'm going to make smaller dots than that. Oh, that's already set on small. Okay, so because there's only two arrows, there's two terms. So we can say Q condense plus Q heat water. And I'll put water or liquid. Those have to add up to 0, okay, because we're just exchanging heat between the two pieces. Then we're going to put in some terms here. So condensing is going to be the amount of water that condenses, we'll say N vapor that condenses, times the heat of vaporization. All right, what about the heating up the water? Well, that's going to be an MCAT because we're actually changing temperature for that purple arrow. So it's going to be the mass of the water, it's supposed to be a W, not an M, the specific heat of the water, and delta T for the water. So the change in temperature for the water. So we have to now put this, we got to make sure these are all variables that are either variables from the problem, so symbols from the question, or symbols for constants that are given on the equation sheet. So a constant's a number. So if we have something like delta H equals 40, delta H vaporization equals 40 kilojoules per mole, we can use delta H vaporization because it's a symbol for a constant, it's a symbol for a number. And we can also use symbolic questions that are given in the question. So let's see if we can fix this here. So we start, I'm just going to rewrite it over here. We've got N vapor times delta H of vaporization plus, now when we look at this, we're like, wait a minute, the mass of water was given, the problem, right? We said we had some mass of water, and the delta H of vaporization is given on the equation sheet, and the specific heat of liquid water is given on the equation sheet. But delta T water, what's that? How much does the temperature have to increase? Well, we are TW degrees below the boiling point. So that's how far up we have to go in temperature. So some of you called it delta TW. You put a delta in here, and because the wording wasn't clear that that was the temperature difference, you could have it either way. It's fine. So you got TW. That's going to equal 0. So looking at these, we know that one of these has to be positive, one has to be negative, and if they're not, then we've made a sign error. So let's go through this and see if we made a sign error, because there actually is a sign error that I want to show you here, and then we can fix that and move on. If we look at this, we know that we're putting heat into the water. You can see that the purple arrow is going to the right, so we know that's a positive Q. And why are we putting heat into the water? We're increasing its temperature, right? So the mass of the water, the temperature increase, and the specific heat, those are all positive numbers. So we know this has to be positive. So this number is supposed to be negative, otherwise we can't add up to 0. But if it's just the heat capacity or the number of moles of water vapor that condenses and the heat of vaporization, that would be a positive number, right? So clearly there's a mistake here. And the mistake we made was actually earlier up here. I'm going to go ahead and fix it now. We have to put a minus in here. We're multiplying by a minus heat of vaporization. Why? Because heat of vaporization, remember, is going from liquid to gas. And we're not going from liquid to gas. We're not vaporizing, we're condensing. We're going the opposite direction. So I forgot to put this negative sign in here, so there's a sign error. So let's go ahead and put that negative sign in here. And we can see, aha, if we multiply the heat of vaporization, which is around 40 kilojoules, times a negative 1, times our moles of stuff that condenses, that will be a negative number. So now we're good to go. So if you have two terms, it's a little bit more complicated when there's three, But if you have two terms, then one of them has to be negative, one has to be positive. If there's three terms, you know that at least one of them has to be a different sign from the other. So this gives you a quick way to check for sign errors before you get to the end. You can also check at the end, but this saves a little bit of work. Okay, so we've got our final terms here. So let's go ahead and we'll put, we'll just rewrite this as N vapor delta H vapor. Just pull that negative sign out in front, looks a little neater. And then we're going to subtract both sides of this term here. So subtract it from the left-hand side and the right-hand side, minus MW, CW, TW. And then we'll just multiply by -1 just to get rid of our negative sign. Okay, now we're not quite there yet because we wanted to have everything be either a constant we could look up on our equation sheet. So let's go ahead and see what is a symbol for constants. That's okay to have in our answer. And symbols from the question. So a constant's a number, right? So if you have the specific heat of water or the heat of vaporization, that's a constant. Okay, so if it's a symbol on your equation sheet that stands for a single number, that's a symbol for a constant. So those are legal to have, as are symbols that are given in the question. So let's see if we've fulfilled that yet before we start doing our algebra. So constants that are on the equation sheet, specific heat of water, the heat of vaporization, those are on the equation sheet, so we can look those up. What about symbols in the problem? Well, TW was given in the problem, and the mass of water was given in the problem. But N vapor, that's not given in the problem, and it's actually not what we want to solve for. We're not supposed to solve for how much vapor condensed. We were asked to get the mass, not how many moles. So we want to somehow change N vapor so we can match the constraints of the problem. So the moles of vapor that condense is the mass of vapor that condensed divided by the molar mass. And you can use M over bar or MM or any symbol as long as it's clear what you mean. So if we divide the mass by the molar mass, that gives us the number of moles. That's the same as N. So we're just replacing N with that. And now we rewrite this. And notice now everything in the problem is either a constant we could look up, or it's something that's given in the problem. Or actually, constant we can look up includes molar mass, right? Because we've got a periodic table. So the only thing that is not a constant we could look up, or something that's on the equation sheet, or a symbol from the problem, is the mass of vapor that condensed, and that's our unknown. So the only thing left over is the unknown. So we're ready to do our algebra now. So now we're going to, we got to get rid of heat of vaporization. So our goal is to isolate this, right? That was the thing we're going to solve for. So we're going to divide by delta H of vaporization. And we want to get rid of the molar mass, and so we're going to multiply both sides by molar mass. So we could, I don't really need parentheses, I'm just putting it in there to show that we added that on. Okay, you don't need the W on there, I don't know why I put the W on there. There we go. Well, actually I want to say that it's water, let's put it back on. Okay, molar mass of water specifically. Okay, so that would leave us with the mass of vapor that condenses. So let's see if this makes sense. First of all, if we plug in all these numbers, we get a positive number. That's good. We know some of the water does condense. This says that the further we were below, remember TW is how far we are below the boiling point, the more water is going to condense. So the more cold the water is, the more the vapor is going to condense when we mix it with it. Okay, that makes sense. The more cold water we have, the more water vapor is going to condense. That's true too. Okay, and you can think of the heat of vaporization as how hard it is to do the phase transition, how much energy you have to do to boil the water, or how much energy you have to pull out to get it to condense. So the bigger that is, the less of it's going to condense. So this looks like the right answer. And indeed, this is the right answer. Oh, we should check the units. If we used, just to check the dimensionality, we're not going to actually put units in here, but we can see that if we use typical units, we'd have grams, we'd have joules per gram per degree C. We've got a temperature change in degree C. We've got a molar mass in grams per mole. And we've got a heat of vaporization in joules, or we could change it kilojoules, but we could change it to joules per mole as well. And if we look at all these things, we can see that the joules are on the top of the top and the top of the bottom. That's going to cancel. Grams are going to cancel here. Per mole on the bottom and per mole on the top are going to cancel. And our degrees C on the bottom here and top are going to cancel. And we're left with grams. And we wanted to find the mass in grams, so that works. So now we're really confident that this answer is right. That's the end of the key. Thanks for watching.